And also flow theory can have some other applications in matching theory. Many matching theorem in bipartite matching theorem can be easily proved by using this flow theory. So again, let's briefly recall. So matching is in a graph G is set of pairwise non-incident edges. So we have these several edges, then this is a matching. But this is not a matching because this edge and this edge are incident. They share the vertices. They share a vertex. So they are not matching. And it is also called independent edges. And we say a matching covers the vertices in each edge. So this matching covers the vertices V, U, W, V, and V prime, U prime, W prime, but say not X. And if a matching covers all the vertices of G, then we say that this is a perfect matching. So perfect matching in G. Perfect matching of the G or in G. And we write the alpha prime G to denote the maximum number of edges in a matching in G. So size of the largest matching in G is write as alpha prime G. So if alpha prime G is exactly the half of the number of vertices in G, that means G has a perfect matching. So that's the equivalent condition. And also we say a vertex cover of a graph G is the set of vertices which having at least one endpoint of every edge. And the vertex cover number, beta of G, is the minimum size of a vertex cover in G. So for example, we say this X is a vertex cover, then that means that every edge is either inside of X or have one endpoint in X. So there are no edges inside this set. Then no edges in outside X is same as X is a vertex cover. So perfect matching is the set of edges which meets all the vertices. The vertex cover is the set of vertices which meets all the edges. So they are kind of dual each other. So this duality is actually giving us, this duality is actual thing, at least for bipartite graph, which is what we learned in undergraduate graph theory, which is called Koenig theorem or Koenig-Ezervary theorem. If G is bipartite graph, again, we all know what bipartite graphs are. Bipartite graph is a graph which can be partitioned into two independent sets. Every edge is between them. If this is bipartite, then we have the size of perfect matching, size of largest matching is same as size of minimum vertex cover. So this can be proved in various ways, and one of the ways is using flow theory. So let say AB be a bipartition. So sometimes we write bracket A, B, or sometimes we write A union B, but we all know what it means, so this is clear. So this is a bipartition of G. So that means we have A, and let's draw it in bigger way. We have A, and we have B, and then all the edges are between those two. What do? We consider a network. Of course, to use the flow theory, we have to consider a network. And for network, we need to have a source and sink. So there should be these two special vertices. But in this case, it is not clear which vertex of G should play the role of source and role of sink. But instead of that, we have two vertex sets, A and B. So that motivates us to give the two new vertices, which are source and sink. And then one is all connected to A, all the vertices in A, and one is connected from all the vertices in B. And then we orient all the edges from A to B. So we consider a network obtained from G by directing all edges from A to B. Because this is bipartite, all edge has one end on A and one end on B. So this defines the direction in a consistent way. All the edges now have the direction. And we add the source S join to all vertices in A, and the sink T to which all vertices in B are joined. And then we want to assign capacity. Let's say, M is some number larger than the number of vertices in G. We can just assign infinite capacity, which is same. And we assign this M, this large number, or infinite, to all the original edges of the G. And assign 1 to all this new edge. So this is the situation. Now, what happened? Because all the values here are 1. So for all the vertices in A, the incoming flow is at most 1. So it can emit at most 1 flow to outside. From that, if we have a maximum integral flow, then that's actually how it looks. Is from S, you have some 1. So flow value 1, 1, 1 are going out. And then, because this vertex now gets 1, so it has to emit 1. If this is maximum integral flow, there is no way that it can emit anything other than 1. It's either 1 or 0, but if it gets 1, and it actually has to, make the 1 going out. And then the corresponding vertex also sends 1. So maximum integral flow actually corresponds to a maximum matching. In a converse way, if we have a matching, that corresponds to, in a natural way, that corresponds to flow with the same value as the matching size. If you have a maximum integral flow, then that corresponds to, if you have an integral flow, then that corresponds to a matching. And if you have a matching, then that corresponds to an integral flow. Then maximum integral flow corresponds to the maximum matching. The the maximum matching corresponds to a maximum integral flow, and a minimum couple. Let's see what minimum couple corresponds to. To a minimum sourcing cut. Because, why is it? Because if we have this A and B, and then assume we have this S and T, and then assume we have source sink cut S and T, then what's the value? What's the, capacity of this cut, source sink cut? So all the edges here are in the cut, and all the edges here are in the cut. They have all capacity 1, 1, 1, 1, 1. And we don't care about the capacity inside of this S, and we don't care about the capacity inside of this AB, and we don't care about the capacity from this to here. But as soon as we have a edge from this set, which is A intersection S, and this set is B intersection T, as soon as we have one edge here, that's counted as a cut. But how much is the capacity of this? It's M, which is large. So if this is the situation, then this ST is not a minimum cut, because it's worse than S union, worse than this trivial cut. S is just one vertex S, and T is rest of them. Or we could take everything in the other way. So this pair or this pair, that gives us a cut. But what's the capacity of this cut? Capacity of this cut is size A, and the capacity of this cut is size of B. Because in that case, if we partition it in this way, the edges in this cut are all these edges, and all of them have the capacity 1. If you add them up, then that's exactly size of S, A. But what did we say? This M is bigger than A, and M is bigger than B. So this is bigger than the number of vertices in G. So as soon as we have this one edge, then capacity is bigger than M. So this is never a minimum cut. So what would be a minimum cut look like? Minimum cut would be that be that in a minimum cut, there are no edges between this A union S and B union T. A intersection S and B intersection T. So in that case, A intersection T and B intersection S. So this set and this set will meet all the edges because there are no edges here. So every edge is either here or here or here. Those three types of edges. They all intersect. They all incident with one vertex in this set. So this is a vertex cut. At the same time, the capacity of this cut is exactly the number of edges sending here and the number of edges sending here, and which is same as size of this size of this set. And because of, these two trivial cuts, we know that there exists a cut which does not use any edges of capacity M. And among those, we take the minimum one. Then that minimum one has the capacity same as one of the vertex cover. And conversely, if we have a minimum vertex cover, then we put that vertex cover, we divided it in two sets. The ones that belongs to A and the ones that belong to B. And then the ones that belong to B goes to, this set S. And the ones that belong to A goes to this set T. And then distribute the remaining vertices as in this picture. Then we get the source sink cut with the capacity as this size of the minimum vertex cover. So this shows that a minimum cover in G corresponds to a minimum source sink cut. So as an exercise, you can write in a more rigorous way by yourself. So what do we know? So by the by the max flow Minko theorem and then flow integrality theorem, what we know is that the size of minimum source sink cut is same as size of maximum integral flow, which is say that the maximum matching size is same as the minimum vertex cover size. So this proves the theorem. So this proves the Koenig theorem. So using this max flow Minko theorem and flow integrally together gives it's quite useful for us. It gives us lots of application. We can also prove a whole theorem using this. So what's whole theorem? So we also learned it in undergraduate graph theory course. Let G be a bipartite graph, say with bipartition A and B. Then this G has a matching covering all the vertices in A if and only if for any subset X of A we have the size of neighborhood of X is as large as the size of X. So let's prove this. So necessity is clear, because if we have a matching, then whatever set X we take and consider its neighborhood, then these, partners of these vertices must be included in the neighborhood. So its neighborhood must be at least as big as the original set X. So we only have to prove the sufficiency. So this shows that we just show that this condition is necessary for the graph to have a matching covering A. Now we want to show that this is sufficient. So suppose for all set X, we have the condition that its neighborhood is as large as the set X. Then now we want to show that it contains a perfect, matching covering A. So how do we do it? We want to turn this into a network, and then we use the Max-Flow-Minko theorem to prove that there exists a perfect matching. So how do we do it? Is we turn the graph G into a network, as in the previous proof of Koenig's theorem. Meaning that we have this A and we have this B, and then all the edges are directed this way, and we have source and sink, which is connected from and to B and A. And then all the capacity here are large and capacity here are 1. This, trick of giving large capacity to certain edge to, avoid usage of these edges in a cut is, it's quite useful technique in many ways. So, again, it's clear that if there is an integer flow of, say, value same as size of A, then the edge with value 1 forms a matching covering A. So this is pretty clear. So, and we are done. Otherwise, if such an integer flow doesn't exist, then what does it mean? By Max-Flow-Minko theorem, there exists a sorry for the noise. While I'm recording this, I'm in my office, and sometimes I forgot to turn off the phone. So otherwise, Max-Flow-Minko theorem says that there exists a cut, sourcing cut, St of capacity, say K, which is smaller than size of A. Then what happened? So we have this A and we have this B, and again this is S and this is T, and this capacity is smaller than A, so that means we have S and T, the number of edges here and here together are K, and then there are no edges here. So let's write this S intersection A, S intersection B, T intersection A, T intersection B, and there is no edge between A intersection A, T intersection B. Otherwise, this cut has size bigger than M, which is far bigger than this K. And we know that the size of this together with size of this are K. So we know that A intersection T plus B intersection S is K, which is smaller than A. And what's the size of A? A is A intersection T plus A intersection S. So this and this we compared, and then the letter is bigger. We delete the same term, then we say we get the A intersection S is strictly bigger than B intersection S. So let X be this set, A intersection S. Then what we have? We have neighborhood of X is subset of B intersection S, because this set, all the edges from this set are going to here. There are no edges from here to here. So this contains all the neighborhood. What does this mean? Say, let's write it as otherwise there would be an edge with capacity more than, say, K crossing from S to T. Thus, what do we get? The size of neighborhood of X is smaller than or equal to B intersection S, which is strictly smaller than X. This is violating Hall's condition, which is a contradiction. So this proves the Hall theorem. And page 9. And from this we can, in the undergraduate graph theory, we proved the defect formula. In an AB bigraph, bipartite graph with the bipartition X, A, and B, we have the size of largest matching we can actually determine as measuring the size difference between the set S and its neighbor. So Hall's theorem says that if X minus the neighbor of X is always non-negative, then we can have a perfect matching. And then here is you take this value, and then even if this is some non-negative, you take the maximum value of this and then subtract it, then that gives you the size of maximum matching. let's move this to later. Let me do this. So we just proved the whole theorem and defect formula, and